Hello, Professor. My name is Ilyas Lahafi. This is my first assessment for the computer architecture and organization. I'll be answering or try to answer the three questions and link each back to our intended learning outcomes. So before starting, here's my computer, which will be the baseline for our analysis. It is a Lenovo ThinkPad T490S. It's an Intel Core i7, 4-core, 8 by 8 threads, 1.9 gigahertz base, 16 GB RAM, 512 gigabytes SSD with an Intel 620 GPU, and the display and the 720 pixel camera webcam, which you're seeing me with right now. So, starting with the first question, uh, transistors scaling and frequently growth powered early generations. So when power or thermal limits hit, architects shifted to multi-core, larger caches, specialized units, and packaging tricks. My laptop embodies that shift, my Lenovo. It uses a low-power mobile i7, which is designed for energy efficiency rather than pushing single-core gigahertz, an integrated graphics, and a DDR4 memory. And this actually shows the trade-off. Instead of for much higher clock speed, vendors deliver throughput and energy efficiency via core and micro-architectural improvements. So when it comes to the history of the computer generations, uh, historically, the first generations of computers used the vacuum tubes, which we talked about. They were large, consumed enormous power, and generated heat, which made systems unreliable. The second generation, shifted to transistors, which were smaller and more efficient, but still limited in density and speed. And for the third one, which is the integrated circuits, uh, it combined many transistors on a single chip, which reduced size and cost while boosting speed, but it was eventually scaling these circuits. These circuits still faced physical and economic challenges. We can say that, yes. When it comes to the Moore's law, historically, it predicted transistor count doubling that enabled higher clock speeds and features. But today, the physical limits, which are the leakage, the heat, the diminishing returns from frequency scaling, it means we get performance from parallelism, which is like just more cores, deeper and smarter caches, and specialized accelerators, GPUs and NPUs. Now, my T490S, which is a model of my Lenovo, demonstrates this. It's a modest core count and base clock, 1.9 gigahertz, but good multi-threading and big caches to balance battery life and sustainable performance. So for the progression and limits point here, Moore's law still guides transistor budgets, but the performance story is now about architecture mostly. The core count, cache hierarchy, and specialization, not just raw clock speed. What's important, as I said, is the architecture, the core count, and the cache hierarchy and specialization. This explains why mobile CPUs prioritize IPC, power envelope, and integrated features over pushing just single thread gigahertz. Now, for the second question, let's walk through what happens with an instruction like add 100. This means we are adding the constant value to whatever is already stored inside a register. Registers are the fastest storage locations inside the CPU. They sit right next to the execution units and can be read or written in a single cycle. If the needed value is already in a register, the CPU can access it almost instantly. If it isn't, the CPU may have to fetch it all the way from the memory, which takes far longer. This process begins with instruction fetch. The program counter, PC, keeps track of which instruction comes next. The processor first looks for the instruction in its instruction cache, the L1, and if the instruction is found there, it moves immediately to the pipeline. If it is not, the CPU has to fetch it from the deeper levels like L2, L3, or even the main memory, which is the DRAM here. Each step down adds more delay. A cache hit is quick, but a cache miss can be hundreds of times slower. Next comes decode. The bits of the instruction are fed into the decoder and control logic. The decoder recognizes that this is an add immediate instruction, meaning it needs to add the fixed value 100 to the content of the register immediately. At this stage, the decoder generates the micro operation that tell the rest of the CPU which register to read from and how to supply the constant 100 into the arithmetic logic unit, which is the ILU. Then we reach the operand fetch, which is the second step. If the operand is already in a register inside the register file, the CPU simply reads it directly. This is the best case. Since registers are right inside the CPU core and give the fastest possible access. But if the register's value had previously been stored out of memory, maybe due to limited register space or multitasking, for example, then the CPU must perform a load operations. That means bringing the data all the way back from the DRAM through the L3 cache, through the L2, then into L1, and finally into the register file. Now, compared to a direct register read, this memory path is much slower and introduces serious latency. Once the operands are ready, the execute stage begins. The ALU performs an addition. It takes the register value as the constant 100 and produces the result. Modern processors can handle an immediate add, like this is in a single execution step. An advanced microarchitecture may even reorder operations or dispatch them out of order to keep throughput high. And finally, we go to the write back stage. The result of the addition is written back into the same register in the register file. Now the updated value is available for the very next instruction that needs it. Meanwhile, the program counter, PC, increments, so the processor knows the fetch and execute the next instruction in sequence. Now, what makes this instruction faster or slower? Instruction speed depends on where data is and how the CPU handles it. Registers and caches are fast, but accessing main memory can stall hundreds or thousands of cycles. Higher clock speed help, yes, but deep pipelines and stall can reduce gains. Out of order execution hides some delays, while interrupts and context switches add extra latency. Now, for example, an add to 100 using only registers is almost instant. But if the operand is in memory, it can take much longer. That's the problem. So, for the third question, for the next decade, I think after doing some research, I think it belongs to the heterogeneous chiplet-based architectures with accelerators. Looking forward, Moore's law is slowing as expected, and many expect its end within the next decade. Instead of simple transistor doubling, progress will depend on new paradigms like chiplet packaging, 3D stacking, heterogeneous architectures, and domain-specific accelerators. The future of Moore's law isn't about raw transistor counts, but how those transistors are organized and specialized to deliver usable performance. Chiplets allow multiple dies, yes, combined in one package. Accelerators like GPUs and NPUs handle AI and graphics. 3D stacking puts memory on package to overcome bottlenecks. And this shift is necessary because Moore's law scaling is definitely slowing. CPUs act more as coordinates while specialized blocks do the heavy lifting. Now, in my case, for my Lenovo T490S, it actually lacks accelerators. So for the ML or graphics, I should and I definitely need to rely on cloud services or eGPU through, for example, Thunderbolt. And this contrast shows why accelerators and packaging will dominate in the next 10 years, inshallah. Thank you, Professor, for listening, and hope you have a great day. Thank you.